Hello, my name is Katherine Kim. I'm a professor at National Taiwan University and currently the Vice President for Global Relations for the Power Electronics Society. In this video, I'm going to be talking about the basics of photovoltaic modeling and how we use that to interact with DC-DC converters for photovoltaic applications. Here we're going to be talking about solar photovoltaic cells. First, how to model them. So let's look back to what a photovoltaic cell is. And we're going to come back. First, we're going to start with just a PN junction here. And we're going to have our P on the top part and N on the bottom. I'm going to draw a little junction here. And recall when we have a p-doped substance next to a n-doped material, they're going to form a little barrier. And we're going to have some positives on from the p side go to the negative side. We're going to get a little depletion region here. And we're going to have some negatives as well that are going to come from the n side to the p-doped material. And what we get from that side, from this region, is we get an electric field. So we have an electric field going here. And this is simply a diode. Let's just remember the diode goes generally in this direction for the component. And what happens is that when we have a photon coming in externally, so let's say a photon is coming in here, it has some energy. It's going to excite an electron from the valence band into the conduction band. And so we're going to get a little negative charge floating here. And the place where that electron left is going to leave a little positive charge as well. So those are going to be created in that electric field. The positive is going to go with the electric field. The negative is going to go in the opposite direction. And what that creates is a charge. So what we'll get if we connect something over it is we're going to be getting current out of it and some voltage over it as well. And so this is the basic principle of the photoelectric effect that we can get from a small PN junction. For a solar cell, what we want is we want a large area so that this electric field is over a really large area. So instead of a tiny diode like we're used to, a tiny component, we're going to extend this, so make it as long, as flat as possible with a large area. And then you can see you would get a larger depletion region. And so you can capture more of those electrons. And so if you see a panel tends to be large and flat. It's the PN junction large over a large area so that lots of photons coming in can get captured and go into this electric field. So now we know how the photoelectric field works, but we want to now use that for power electronic converters. So we need to transform that concept into electric circuit components so that we can model it and simulate it. So I'm going to draw something similar to what we just had. A large PN junction. So P on top, N the bottom. A large junction there. And when we have these two together, we're going to have a basic diode. So I'm going to draw the diode. Actually, remember, it's going downward here. So this is the basic component that we're getting. And we also had the photoelectric effect. So the photoelectric effect, this is from when the photons were coming into the material, is creating a current actually that's coming out. So we model that as a current source. That's coming out here. Okay, so those are the two basic components that we use to model a photovoltaic cell. I will mention that there are actually some other things going on in this circuit. There's going to be some resistance between the P and the N, positive and negative terminal. There's also going to be some resistance that happens coming out of the circuit. And if we want to get into the advanced modeling, we'll also have some capacitance and some inductance at the end as well. So this is our advanced model, but we are just going to focus on this ideal model. So this is the ideal model for the PV. And I will mention that generally the photons are going to be coming into the N side. That's just how they manufacture them. So if we have light coming in here, usually hitting the N side, and then we're getting a positive coming out here as our voltage, that would be our VPV, and then our current will be coming out here and follow that around our whatever our load is going to be. And so the current is going to be coming out of here, so IPV. All right, so we're going to focus on this ideal photovoltaic model and go a little bit more into what that looks like in terms of IV characteristics. So from this model, we're going to redraw that here. So we have a current source. I'm going to call that IPH for the photo current. And then we have our diode going down here. And this again is based on the PN structure of the photovoltaic cell. And let's look at the IV characteristics of each of these here. So if we're looking at the voltage and the current, this is a current source. So whatever the current source is going to be, it's going to come out maybe like that, and at the level of IPH. All right, and then let's look at the IV characteristics of just the diode real quick. So we know a diode characteristic has generally zero, goes through zero, and then it's going to be going upward like this and continue upward like that. If we look at the currents that are going through here, we have the IPH is actually the current coming out of here, and then the diode current is going down this way. So I'll label that as ID. Then the current coming out of the photovoltaic cell itself, so IPV, that is going to be this photocurrent, IPH again, here minus ID, that will give you IPV. So if we're thinking about this in terms of IV curves, we would take this current minus, in a sense, minus this, and what we'll get at the end is, what this value was, minus a current like that, and we'll get something that looks something like this. So this is the voltage and current for the PV. And we'll notice this is a non-linear characteristic, and that it will not necessarily create power at all of the points. If it has zero current here, for example, at this point, this is called the open circuit voltage, VOC, or it's operating here. This is the short circuit current, I short circuit. There's going to be no power. And if we do the calculation for this, we'll see there's one maximum, we call this the maximum power point, that is right near the knee of the curve. I'm going to briefly draw this for the power versus the voltage, just to give you a sense what it would look like. So this would give you the power versus voltage curve for a illuminated solar photovoltaic panel, and then this maximum point would be the maximum power point. So this is great. We can model this photovoltaic panel using electric circuit components, but how do we interact that with a converter? So let's talk about that next. When we draw a simplified component of the PV panel, we generally use this type of little symbol here. So this is the PV cell, or it could be a module. We represent it like this in a circuit. And then we want to connect that then to a converter. What we'll do is we'll connect it to some sort of converter. I'm just going to draw a big box here. We'll just fill this in a second. And we're going to have some sort of a load, which I'm going to just draw as a general load right now. So this is going to be our load. So let's say that we have a buck converter inside of here. So I'll just put a DC converter. And let's say that we have a buck converter. And we'll put a capacitor here. We have a buck converter, and we would then connect that to our PV cell as our input. Inside of this PV cell is going to be our diode model. I'm just going to redraw it here. And I'm going to draw a few additional resistances that are often modeled. And you can look this up. This is called the single diode PV model. But as you can see, it's just our ideal model, which is here with some additional resistances. So we can model that as the photovoltaic cell. That's what's inside of here. And then we can model our converter around it. If you're simulating, you can usually find some models in many simulation software that come as a block. You do want to check and see what kind of model they have. They may have a very simplified ideal model, or they may have a more advanced diode model of either a cell or a module. Attach that and you'll have a DC-DC converter. The important thing I want to emphasize is that when we're using a diode, the power, again, is variable. So I'm just going to draw the power here really quickly again. The power is not always going to be exact. So depending on how this is controlled, how much voltage is coming out of it, the power will also be varying. So you may not get exactly the voltage or current that you want depending on the characteristics of this converter. And that's where the control comes in. So I want to emphasize two things. One is control. When we have a DC-DC converter, conventionally, we're often taught that we're controlling the output. And in this case, though, we are not usually controlling the output, we're actually controlling the input. So we would be controlling either the voltage or the current or the impedance characteristics of the input to control this PV cell at the point. Say we want to go to the maximum power point. And so you will be controlling the input, and often you'll be using a maximum power point tracking algorithm to do control on the input side. You may say then, what happens at the output? Don't I have to still maintain a constant voltage? When you control the input side, what happens at the output is going to be pretty much a power balance. So your load may be, it could be a resistor. That's often where you start with a very simple control, or it could be a type of battery, which is often photovoltaic to a model is a very normal application. In that case, you may simplify the battery to be a voltage source. So in that case, whatever power you're operating at here is going to be going into your load, and depending on what type of load you have, your voltage and current will adjust to meet the power balance. So control for a DC-DC converter that's controlling a photovoltaic cell will focus on input side control. The other thing I want to mention for these types of circuits that sometimes students run into are the protection. Because inside of this PV cell is actually a diode pointing downwards, so there's a diode going from here to here, if your load is a battery, and you're not quite controlling your converter correctly or something else is happening, you may actually get current flowing from the battery to the input side because of this body diode here. So current can flow backwards. And so if you want to protect and avoid the current going backwards, you can add a protection diode here to prevent current flowing backwards. That I've seen that happen with students making a circuit and then losing all their power from the battery once they connect the PV cell. The other thing and to mention is a bypass. So if we have multiple cells in series, we can bypass each of them, and the bypass diode would be going around in this direction. That's when we want to completely bypass this diode because the current is either too low or insufficient. So that would provide a path for the current to flow around the cell. So this would be a bypass. As a quick summary, we have a photoelectric effect happening from the PN junction. When we model that, we model it as a ideal diode and a current source, and we can add some other dynamics to it as well. The common model we use for that is a single diode model. It has one diode and two resistors, and one in parallel and one in series. That will be your model for your cell. And then when you're designing your DC-DC converter around that, you have to remember that your power is going to be nonlinear. And so when you're controlling the input. We often are going to use a maximum power point tracker for that. And other things that we can keep in mind are we can have some protection for the diode to prevent reverse current flow and a bypass around a cell. That's usually when we have multiple cells connected in series. This is a quick overview of how you can model a photovoltaic cell and then use it to understand and simulate DC-DC converters for photovoltaic applications.